All right, let's take a look at the RC circuit. So what we have here is we have a battery that can produce a potential of V. We have a resistor, and then we have a capacitor with capacitance C and resistance R. Okay, and we're going to flip this switch and we're going to charge this thing. Okay, so we're going to look at charging and then we'll look at go ahead and discharging it. Okay, so let's start out with the differential equation, and again we get this from knowing the loop rule. So Kirchhoff's loop rule, which is really a conservation of energy idea, says that the sum of all the individual voltages have to equal 0. And what that says is the gains have to equal the losses. And so what we get here is we get a voltage gain, a potential gain by the battery. We lose a certain voltage over the resistor, which we know over here that V equals IR for a resistor. And we also know that Q equals CV. Those are kind of just the definitions, but at this point you've used these things 1,000 times. That this is the voltage over a resistor, and this is the relationship between charge, capacitance, and voltage over a capacitor. And so the capacitor drop in voltage is going to be Q over C. And that equals 0. Okay, so let's think about the beginning here. Right when you flip the switch on, right away, is there any charge on the capacitor? Well, no. So this term is 0 at the beginning, and so all of the voltage drop is over the resistor, which means that's when the current is at a maximum. So I guess I should draw another picture down here and kind of like go over schematically what's physically happening here. And again, you're charging this capacitor, and the capacitor will eventually then reach the voltage here. So this is some voltage, and it does work on charge in it. So it's sending all these charges this way, right? So current is being sent this way around our circuit. And what's happening here is you're taking positive charges from here, and what you're doing is you're placing positive charges on this plate. Okay? And that leaves then negatives down here. And the battery continues to do work, and so it continues to put more and more charges on this plate and leave then the bottom plate more and more negative, because conservation of charge says that if we take charges from here and put them up here with them, this is left as a negative and this is left as a positive. And then eventually what happens is you have enough charges on this plate that the plate's voltage is equal to the battery voltage, and then you're in some static equilibrium. Nothing can happen anymore. The battery can't produce a higher potential on the capacitor than it has in itself. So then we would say it is fully charged. And when it's fully charged, there's no more flow of current over the resistor, and so eventually this current goes to 0 and this is fully charged. So if you looked at the graph of those things, we actually should have a pretty good idea of the current as a function of time and the charge as a function of time. Okay, so what would the current look like? Well, when there's no charge on the capacitor at the beginning, it's really easy for the battery to start making the current flow through the resistor and to start accumulating. So at the beginning, this is actually at a maximum. Now, what is that maximum? Well, this current at a maximum is actually just V over R. Remember, just set this equal to 0 at the beginning. At the beginning, no charge on the capacitor. That's 0. And so then the current is just V over R, right? It's like the capacitor's not there. So we'll put some maximum current that we know is V over R. And then what is it going to do? Well, look at it. Eventually we can show that the math is that it's exponentially going to decay to 0. Now the charge on the capacitor is 0 at the beginning. And think about, is it easier to accumulate charge at the beginning or at the end? Well, once this capacitor starts to get more and more charge on it, it actually becomes more and more difficult to put more charge on it, because these positive charges don't want to be next to each other. Right? That was Coulomb's law at the very beginning. Like charges are going to repel each other, so this battery has to do more and more and more work. It's more and more difficult to charge this thing once it gets to have some charge to accumulate on it. So this curve should make sense that it eventually asymptotically approaches some value, some maximum charge, and then it's easier to increase the charge at the beginning and harder and harder and harder at the end. Okay, now what is this maximum charge? Well, just look at it. Eventually this gets to the same voltage of the battery, and so this maximum charge is just CV, the capacitance of the capacitor times the voltage of the battery, right? The bigger the capacitor, the bigger the battery, the more charge this will store eventually. Okay, so we know that the two graphs are going to look like this. We just have to make the differential equation work itself out, and we can see then these solutions. The calculus I want to point out is, remember, what is I? I is the flow of charge, dq dt, and this is the current through the resistor, so it's the rate at which the charges are flowing through the resistor, which is equal to then the rate at which the charges are actually accumulating on the capacitor. So we can relate these two quantities. Okay, so what I'm going to do is I'm going to, this thing here, this dq dt, I'm going to move to the other side of the equation, and I'm going to leave this guy. So V minus Q over C equals IR. So I just put the I on the other side, but I'm going to write it as dq dt times R. I'm going to divide everything by R. This is then RC. This is then just equal to dq dt. I'm going to make this one fraction, so I'm going to put a C here. So put a C here and put a C here. Okay, so that's VC minus Q over RC equals dq dt. And now I'm going to use separation of variables. Separation of variables is a classic way to solve separable differential equations. So I'm going to leave this RC, a 1 over RC, and the dt are going to be on this side. 1 over RC dt equals dq all over dividing by this VC minus Q. Okay, I now have the variables separated. The variables are time and charge. R, C, and V are all constants. They're not functions of time. So I've separated the variables, and now I'm going to integrate. The integral of 1 over RC dt is just 1 over RCT plus some integration constant. I know it's a little confusing. This sees capacitance. This sees an integration constant, which we'll figure out here in a second using an initial value. And over here I get some logarithm. This is like a du over a u. That negative sign is going to give me negative natural log of Vc minus Q. Again, think of the chain rule. We know that at t equals 0, Q equals 0, because we know that the capacitor started uncharged. That's going to allow me to find this. So what I'm going to do here is I'm going to plug in t equals to 0, which makes that term 0. And I'm finding what C needs to be, negative natural log, and Q equals 0, Vc. So now I know what C is, right? So I get 1 over RT, 1 over RC T minus negative natural log of Vc equals negative natural log Vc minus Q. Okay, now I'm going to get rid of this negative sign. Okay, I'm going to multiply everything by a negative, which makes that a positive, and that a negative. Now I'm going to exponentiate, which means I'm going to raise both those things as a power. And this is e to this plus this, which is e to this times e to this. So e to the natural log of Vc comes out in front as Vc e to the negative 1 over RCT equals, and then here is just Vc minus Q. I'm going to move the Q over to this side, and then so move, add the Q, and then this side is just Vc minus Vc e to the negative 1 over RCT, and then I'm going to factor out that Vc, and then I'm going to get my 1 minus e to the negative 1 over RCT, which is then done. Okay? This equation, again, you may or may not have experience of what this looks like in terms of an equation, but a 1 minus a negative exponential. Remember, as the exponential gets bigger and bigger and bigger, this gets closer and closer to 0, so you end up doing 1 minus something that gets smaller. So at the beginning, this is 1, So 1 minus 1 is 0. And then eventually this gets smaller. And so 1 minus something gets smaller and smaller. Actually, it lets this thing grow a little bit. But it does grow in that shape. And so this is the charge on the capacitor as a function of time. If you took this derivative, and I'm going to kind of run out of space here, but if you took the derivative, then you could find the current through the resistor, because the current through the resistor is dq dt. And so Vc times 1, actually we can go back up to here, it might be easier. The derivative of that goes away, and the derivative here, the negative and the negative will cancel, and then when you take the derivative of an exponential, you're going to get a 1 over RC. Well, Vc times 1 over RC is just V over R. The C's cancel, and then the derivative of an exponential is just e to the u times u prime, and so then you're left with this guy for the current. And so you get some negative exponential for your current, which is what we said, it just exponentially decays, and then you get the whole 1 minus a negative exponential for this curve. And again, I've derived both of these equations, which we knew what the graph kind of looked like. We knew what the limiting cases were at the end, and we knew what it started out at, and these two then confirm. Probably a good idea to memorize those. And again, this is charging an RC circuit. There's different scenarios in that. Again, you need to be able to do separation of variables. Again, I understand that going from here to here is physics, and the rest of all of this stuff is really a calculus class. But that's what happens with AP Physics. You're going to have to be able to relate things that involve some calculus. So as a reminder, if it was something like this, it's no different. The R is just then the series addition, or the parallel addition of those two things. It doesn't really change anything at all, just what the effect of R is. You could have a resistor here and another resistor here. Again, that doesn't change anything. That's just having those two resistors are just in series. Having them on opposite sides is the same thing as just having them in the same thing. So there are things that, little bitty things that they're going to tweak, but it doesn't actually change anything, so you should be fine. And then the last thing is we should talk about discharging. The nice thing about discharging is that the calculus goes really fast, because we're talking about a discharge. So take our situation here, and so you're just going to connect it over here, and so there's this switch, and so this, you're going to take this switch and turn it off, and then over here you're going to turn this switch on, and so then everything's just going to go this way then. And so all you have to do is take that loop rule and just get rid of the battery. So if you write out the normal loop rule that we had, just the fact that if we make that switch so that that wire is not connected anymore, that just goes away. And then here we can go, pretty quick. So what happens here is that this is still we're going to do the same thing. Negative Q over C equals, I'm going to put that to the other side and write it as dq dt R. I'm going to move that R over here with the dt, so it's negative 1 over R C dt equals dq over Q. I've separated the variables. Now I need to integrate. Integrating negative over 1 over RC T plus C equals natural log of Q, except what's the initial value in this case? At T equals 0, what was Q? Well, Q is CV. Remember, this whole thing is charged, and it got charged to a certain voltage, the voltage of the battery at a capacitance C. Okay, so this is what we need to use here. So when T equals 0, that goes away, and we get C equals the natural log of Q, what Q at T equals 0 is CV. So that allows us to find this integration constant. So we have negative 1 over RC T plus the natural log of CV equals the natural log of Q, and then we can just exponentiate, and we're done. E to the natural log of Q just gives us Q, and then this is e to this plus this, which is e to this times e to this, which just gives us that CV out in front, e to the negative 1 over RCT, and as hopefully it's predicted, the charge on the capacitor as a function of time is going to exponentially decay to 0 as you discharge it, which hopefully that makes sense. It starts out being totally charged at CV, and it's going to decay to 0 again. You're dissipating all of that current, all of that energy through this resistor. And then if you looked at the derivative of this, which is the current, you're going to get a negative, and again, CV times a negative 1 over RC. The C's cancel, and you get a negative V over R e to the negative 1 over RCT. Why is the current negative? Well, because it's going in the opposite direction of what it used to. Because now the current is flowing, instead of the current flowing this way through that resistor, now the current is flowing this way. Again, when this thing is charged, it's going to have this potential, and it's going to make everything go this direction. Now up through the resistor instead of the battery making it go down through the resistor, so the current is negative. And again, it's a negative decaying one, so it starts out like here, and the current decays because the current still has to go to 0 because the battery is still going to run out, or the capacitor is still going to run out of charge as it gets dissipated through. Okay, it's done. Okay, so both of these decay over time. This is a positive charge that's decaying, and again, the hard part here is to remember that it's a negative, and it does come out, remember, the derivative of the e to the u is e to the u times u prime. U prime is going to be a negative 1 over RC. CV over RC gives you that V over R. Okay, so this is charging, this is discharging for an RC circuit. They can throw kind of other things at you a little bit, but this is the charging and the discharging. Certainly there are other things you can talk about with a very static situation for what happens after a really long time, and that will likely just be another video. Okay.